It's on, it
Okay.
turns green, and now it's on. Just tap it to make sure it's sounds good.
So now it's on. Okay.
Now it's on. You ready to go, you think? It's just 2.
Yeah, this should be fine. So the clock is there, right? Oh.
Yes, and so it's 1 hour and 15 minutes, so you have until 3:15.
Okay.
And then this afternoon, 3:45 to 5, there's a discussion session. And I think it's just you and Miranda, because Juan flew out
Everybody
today.
else left,
So
yeah.
if there are extra questions, that's a good time for them to do it. Okay, so we can get started for the afternoon session. We're very happy to have Silviu Pufu here from Princeton. He's starting a new series, so you heard a lot the first week from Sheehan about two-dimensional CFT. So Silviu will be talking about the Bootstrap and CFT in dimensions higher than 2. Take it away.
All right. Well, it's nice to be here. I hope I'll get to meet all of you in the next few days. So I'm supposed to talk about Bootstrap and CFT in more than 2 dimensions. I guess that's going to mean that it will be mostly 3 dimensions. Just one at a time. Okay. So just to remind everybody, a CFT in D dimensions is a quantum field theory in D dimensions that has no intrinsic scale. Length scale or energy scale. They're either Lorentzian or Euclidean. So the Lorentzian ones are invariant under SOD, 2. And the Euclidean ones are invariant under SOD plus 1, 1. Presumably people are familiar with this. Yes?
Only for flat space?
In flats, yeah, I'll consider CFDs in flat space. A good question. I'll try maybe on Tuesday to talk about CFTs on the sphere, but I don't promise that. I haven't written that lecture yet. Okay? So, yeah. And for most of the time, I'll focus on Euclidean CFTs. The SOD, 1 symmetries can be organized as rotations, dilatations, and special conformal transformations. Rotations, everybody knows. Dilatations, x goes to lambda times x. And special conformal transformations, you probably don't remember the formula, but it looks something like this. X goes to x minus b times x squared divided by 1 minus 2 b dot x plus b squared x squared, where for dilatations, lambda is the transformation parameter, and for special conformal transformations, it's b, it's a vector. Okay, good. These are quantum field theories, some special quantum field theories. What are they good for? Well, they're good descriptions of critical points. By critical points, that means second order phase transitions. There are actually 2 kinds of these. They can be driven by either thermal fluctuations. That's the case for the Euclidean theories, Euclidean CFDs, Euclidean CFTs, or they can be driven by quantum fluctuations. So if we have some system at 0 temperature and there's some coupling, and we change the coupling, we could have a second order phase transition as a function of that coupling. So that would be quantum phase transitions. They're driven, the phase transitions are driven by quantum fluctuations. So that's for the Lorentzian CFTs. If we have such a thing in a condensed matter system, the speed of light is typically an emergent quantity. It's not actually the speed of light. Okay. Good. So these are new kind of theories, special kind of quantum field theories. This is what they're good for. How can we construct them? So CFTs can be constructed in several ways. One way is explicitly as infrared limits of renormalization group flow. And I'll give examples of this just to give you a picture of what's, for instance, in 3 dimensions, what's known, what Lagrangians give you what CFTs. Well, sometimes we have some indirect evidence for the existence of CFTs. And as an example of that, for an example of a theory for which you don't have a Lagrangian, but we believe it's a CFT, is the 2, 0 theory in 6 dimensions, where there's evidence from string theory. And I guess a third way would be sort of abstractly, if we could. This isn't quite complete, but it would, the way it would work would be by specifying the data needed to describe a CFT. So let's just call it CFT data. Well, we know some properties. I'll explain some properties of CFTs. And you could say that you can construct a CFT that way by just specifying the CFT data, specifying those properties. But of course, you then need to worry about whether you actually have a consistent CFT. So you need consistency conditions. And I think it's fair to say that we don't know the complete list of consistency conditions. Okay? So I think that since this is Friday, the last lecture, today I'll focus mostly on this. And next week, Monday and Tuesday, focus on that. So this is where the Bootstrap comes in.
Sorry, for Euclidean CFTs, we require unitary regression plasticity.
Well, not in what I've said so far. That would be a consistency condition from the point of view of a Euclidean CFT. So if you want to describe, if you have a statistical physics system, then that's not necessary. But yeah, we will be interested in the ones that, then the Euclidean CFTs that can be continued to Lorentzian CFTs that are unitary. Not every Euclidean CFT has this property. Okay. So, yes. Yes. Yeah. For instance, I don't think that the analog of modular, what is modular invariance for 2D CFDs is completely understood in more than 2 dimensions. Well, hopefully, hopefully sooner, tomorrow. Yeah, but I mean, you know, like, who knows, right? Like, who knows what other consistency conditions there are? Okay, so what is this CFT data? Well, it's something that includes what I'll call local CFT data, which is CFT data related to local operators. And I'll take that to mean the local CFT data to be the set of local operators, so the operator, local operator spectrum. By that I mean the list of operators, so list of operators and their quantum numbers under whatever symmetries the theory has, and the OPE coefficients. So for example, and this is a topic for next week, but for example, a scalar operator, well, by the way, so for quantum numbers, I mean the SOD, 1 quantum numbers and the flavor symmetry quantum numbers, just to be clear. So for example, a scalar operator O of scaling dimension delta has a 2-point function O of x1, O of x2, that goes like is some constant divided by x1 minus x2 to the power 2 delta. Okay, more on this later. The question then is, how many CFTs are there? So there are hints that maybe there aren't that many. And I guess the hints come from a very important concept, which is, well, 2 concepts. Scaling, one of them is scaling, and the other one is universality. So universality means that there are very different systems that are described by the same properties. And scaling, I'll explain. So let me give an example, explain by example. I'll give several examples. The first example is a uniaxial magnet, which is just a piece of material where the spins are preferentially oriented along a certain axis. So that's why it's called uniaxial. And they like to be aligned with each other. And we're going to put it in some external magnetic field, H, and measure, oriented along this axis, the preferential axis, and measure the magnetization. Well, probably everyone knows this about magnets, that if I were to draw the magnetization, if I make a diagram like this, where I have the magnetic field on the y-axis and the temperature on the x-axis, there's a region over here up to some critical temperature Tc, below the critical temperature Tc, where even at 0 external magnetic field, there is some magnetization. So this is a spontaneous, so this is the region in which there's spontaneous magnetization. So in this case, the magnetization is non-zero. Well, it could be in the direction along this axis pointing up or pointing down, depending on how the system was prepared. And the idea of scaling is that so for instance, I'm just going to give you a few examples. So for instance, when there's no magnetic field, and we're below this critical temperature, we can measure the spontaneous magnetization, M. So measure M. And what we find is that it's proportional to T minus Tc to some power, and that power is called beta. And we can measure other quantities. And again, we see that quantities behave as a function, for instance, at h equals 0. The various quantities depend on T minus Tc to various powers. And those powers are given, they're denoted by Greek letters. There's alpha, beta, gamma, delta. So that's the idea of scaling, that we have this weird behavior. And another thing I should mention about it is that close to the critical temperature, the correlation length in this material goes to infinity. So if we're close to Tc, but still at h equals 0, we can measure the correlation, we can calculate correlation functions. What we find that they're proportional to, they decay exponentially with the distance. They're proportional to e to the minus the distance divided by some length scale, which is c, that's the correlation length. And the correlation length also depends on T minus Tc as a power law. So it's proportional to T minus Tc to some power. And that power is denoted by minus nu. It's negative because it usually blows up. So nu will be positive. So for example, for this particular system for uniaxial magnets, one finds that beta is approximately 0.33 and nu is approximately 0.63. And if we measure the other critical exponents, I could give many other numbers. Okay? Now, the interesting thing about this is that there is another system. It's okay if I just raise this forward and write it here so that we have them together. So the interesting thing is that there's another completely different system that in some ways it has similar properties. I hope it's still visible if I write on top of this. And that's the water vapor system. So if I draw phase diagram of water, it looks sort of like this. If I put the pressure on the y-axis and the temperature on the x-axis, it sort of looks something like that. So this is ice, or let's just call it solid. This is liquid. Oh, sorry, gas and liquid. We go from solid to liquid to gas, not directly, not the other way around. Well, I guess it depends on how we go. So the idea is that the liquid and gas phases are separated by a line of first-order phase transitions that ends at a point. So it's some critical temperature and critical pressure. And somehow this picture is very similar to that picture. What you should imagine is that this line here, this curvy line, in that picture was made straight and lies on the horizontal axis. But they're really very similar. Okay? How are they similar? Well, for T smaller than Tc, okay, at the first order phase transition point, there is a difference between the densities of the liquid and the gas. So rho liquid minus rho gas is not equal to 0 on either side of the phase transition. Okay? And so that's similar to that. So when we're at the first order phase transition line over here, and there's a spontaneous magnetization. Magnetization changes from one side to the other. The same thing happens here. The density changes from one side to the other. And what's interesting is that rho liquid minus rho gas is, of course, proportional to Tc minus T to the power, we can call it again beta. And there's a correlation length. And this again goes like T minus Tc to some power minus nu. And beta for this is also approximately 0.33, and nu is approximately 0.63. So these two very different systems have the same properties. The same beta, same nu, and if we go through the list of all the other Greek letters, they're all the same. Okay. So the analogy between these two is that the magnetization is like the density. So the magnetization is like delta rho, the density fluctuation. Then the pressure is like the magnetic field, and the temperature is like the temperature. Yeah.
Knowing what we know now about all this, why would we expect these two to be in the same universality class? Learned all of this.
Have learned all of this up until now?
No. All right. Yeah, I guess.
Or mankind up until now?
Mankind. Like, why should water be the same as spin?
Well,
It's not the same as certain other things. It is the same as water.
the order parameter, the thing that acquires a non-zero value across the first order phase transition is a scalar.
A lot of things we care about scalars. A lot of theories are all the theories in the same person.
Right. It's just one. They're two different vacua, essentially, two different phases, one here and one there. The natural assumption is that whenever this happens, this would be in this universality class. Yeah. What's that?
The first order phase transition factor goes across
Yeah. Okay, so I should emphasize that the things that are the same are the things that only very close to the second order phase transition point. Only in this region. Far away from this region, things could be extremely different. And you see that they're extremely different. I mean, this line here is straight. This line here is not straight. This system here has a Z2 symmetry under flipping the sign of the magnetic field. This one doesn't.
How many dimensions is the first system?
3.
Okay.
Both in 3 dimensions.
So is it easy to see that if you turn on a slight magnetic field, there is no second order phase transition? Right.
Sorry, what do you mean?
If you turn on
Yes.
a magnetic field
Yes.
and increase the temperature.
You mean you're You're on the diagram along this line?
Yeah.
Well, the spins want to align. So once you turn on some magnetic field in some direction, the spins will just align in that direction. There's no reason for them to change what they're doing. Okay. So I guess the third system that's just a model, but it has, you can simulate it on a computer, and it also has the same critical exponents, is the Ising model. Yes?
So do the values of beta and nu change if you're working in other than D?
Absolutely, yeah. They depend on D. Actually, the situation for this particular kind of systems, for uniaxial magnets, above D equal 4, the values are all the same. Well, for beta. Okay. So the third system is the 3D Ising model, which is a statistical physics model defined on a 3D lattice. I'm going to draw the 3D lattice just in 2D so that I don't have to draw 3D. And we have spins that are living on this lattice that can take values 1 or -1. And this is just statistical physics. We compute Z as trace e to the minus beta h, where h is the Hamiltonian. It's not the magnetic field. What is the Hamiltonian? The Hamiltonian would be some coupling, sum over adjacent spins, Si, Sj. And if we want to model a magnetic field, we also have a term H times sum of Si, where H is the magnetic field. So this H is not the same as that H. And of course, you get the same HT plot as for the uniaxial magnet. It's not the same as the magnet because this is an idealization. In a real magnet, there are interactions beyond adjacent spins. But the point is that we get the same values for beta and nu and the other critical exponents. So same beta nu for different systems. This implies, this is the idea of universality. This is actually really good news, right? Because that means that, in some ways, it means that we can be very sloppy. We can model this magnet just by that, and even though we're very sloppy, we get excellent results. We get, just get these numbers without any approximation. So it's very different from other areas of physics where, you have a physical system and you try to model it, and then, you compute something, you compare it to experiment, you get something very close, but maybe not exactly right, and then you try to improve your model, and then you get even closer, and then you improve your model, and you get even closer. This isn't what happens here. Here, you can just have a model that's not very precise, but it still gives excellent results. Okay. So the fact that there is universality suggests that perhaps there aren't that many CFDs. Right. So not that many is probably not meaningful because the number is still infinite. But it sort of suggests that maybe not all possible values of the critical exponents of these betas and nus, maybe not all possible values are allowed. Maybe there's something wrong with some of them. Okay. So let me try to connect this to something that's probably more familiar. I don't know if people are familiar with critical exponents, how familiar people are with critical exponents. But the explanation for the fact that all these systems have the same critical exponents is the following. The second order phase transition is described by a CFT with two relevant couplings. So a CFT, for now, you can just think of it as a renormalization group fixed point. So, you know, with the renormalization group, people draw RG flow diagrams, and those RG flow diagrams describe how the couplings change as, say, we change the UV cutoff as we coarse grain. So let me try to actually explain how these beta and nu are related to what's probably more familiar, scaling dimensions. Okay, so in general, so suppose A, well, let me just do it like this. To describe it, to be close to the CFT, so close to the critical temperature, we can have a Lagrangian that's a CFT Lagrangian for the fixed point where the couplings no longer change as we coarse grain, plus some small coupling multiplying some operator H and some other small coupling multiplying some operator T. And let me take these couplings H and T to be dimensionless. So H is like the magnetic field, but the dimensionless version of it, so H over KBT, TC. And T is the dimensionless temperature, so it's T minus TC divided by TC. Okay? And let me consider, for simplicity, let me consider couplings and operators to all be dimensionless. Okay? So then what's the idea with RG? The idea is that we have a UV cutoff, and we change it when we coarse grain. And in order to describe the same system, meaning in order for the partition function to be the same, we have to adjust the couplings a little bit. So if A is the UV cutoff, we coarse grain by sending A to B times A, where B is a number. And just to connect it with what you know, if we take B to be 1 plus something small, let's just call it delta L, then we have to adjust the couplings by a little bit. So we have to send H to H plus delta H, for instance, for the H coupling, the same for the T one. And dH by dL is what's called minus the beta function for this coupling H. So this is what's plotted in the RG flow diagrams. Now, close to the fixed point, so suppose the fixed point is at H equals 0. Close to the fixed point, so the fixed point, the couplings no longer change. So right at the fixed point, beta is 0. Close to the fixed point, it would be linear. And let me write it like this, that beta H is approximately minus YH times H. If the fixed point is not at 0, then this number here would be H minus H at the fixed point. Okay? So what does it mean? So if we plug this back into this differential equation, this implies that close to the fixed point, as we send A to B times A, then this coupling H goes to B to the YH times H.
So what's YH again?
It's this coefficient in the beta function. So the coefficient of proportionality between the beta function and the coupling close to the fixed point. That's what YH is. Another way to think about it is if I'm very close to the fixed point and I send A to a multiple of itself, I would have to send H to B to that power, to the power YH times the coupling, in order to keep the theory invariant. Okay? So the same thing for T. T goes to B to the YT times T. And maybe this is actually enough. But just so that you know what these y's are, the y's are d minus the scaling dimension of the corresponding operator. So for instance, yh is d minus the dimension of OH. I'll explain why this is true. D is the number of space-time dimensions. Well, spatial dimensions, because this is just a Euclidean CFT.
Is this analogous to like where I actually take D equals 4 minus?
No. Well, you can define these CFTs. The closest that I can get to that is you can define these CFTs in continuous number of dimensions. And when you're close to 4 dimensions, there is a fixed point that's accessible in perturbation theory. And for that one, indeed, YH is proportional to epsilon if the dimension is 4 minus epsilon. Okay. So let me try to derive the formula for beta, for instance, and the formula for nu. Yeah.
What does it mean for the temperature change as I report the like temperature? What is this period? Why is it matter by what matter?
Right. Okay. Okay. I introduced T as a temperature, but once we, okay, T is the temperature, then we have some continuum Lagrangian, and then you can just from then on you can just think of T as a parameter in the Lagrangian. And as we coarse grain, in order to keep the partition function unchanged, we have to change this parameter T. For the actual physical system, is some fixed lattice that's not getting coarse grained by itself if we just look at it. And coarse graining is something we do just to understand how the system behaves at larger and larger length scales. So I would say T is just a parameter in the Lagrangian. Or yeah. So this critical exponent beta is defined as the power of T minus Tc at h equals 0. That appears when we measure the magnetization. So let me derive what it is. So the magnetization, by definition, is the change in the free energy per unit volume as we change the magnetic field. And now we should just change it. Just think about how these things change as we coarse grain. Okay. If I want to work with dimensionless couplings, what I'm going to have to write here is, well, I should measure the volume. I should measure the volume in terms of the lattice spacing. So it would be the lattice spacing is proportional to the lattice spacing to the power d. So then, as we coarse grain, as we send A to B times A, what does the magnetization do? Well, because the volume is measured in units of A to the D, if we send A to B times A, it acquires a power of B to the D. And for some reason, I'm confused about it for now. Sorry, let me explain. So H goes to B to the YH times little h. So this would be D minus YH. I can say it in a better way. The free energy is proportional to the number of lattice sites. As if we send A to B times A, yeah, for some reason I'm getting this power that's its opposite. Does anybody see why it's a positive power? Yes. Right. You're right. That's right. So, yeah, right. Changing the lattice spacing, keep the volume fixed, so the number of lattice sites goes up by the power by a factor of b to the d. So then the magnetization goes to the b to the d minus yh. Thank you. B to the d to the minus yh times m. So then, if I want to say that the magnetization is proportional to T minus Tc, or to some power, the power must be such that under this scaling, A goes to B times A, both sides scale in the same way. T minus Tc is proportional to this parameter little t. It goes like B to the yt. Okay? So in order to get something that scales as b to the d minus yh, we have to raise this to the power d minus yh over yt. So this parameter beta is d minus yh over yt. Similarly, for correlation functions, they close to Tc, they go like e to the minus the distance divided by some length scale. If we wanted to measure everything in units of the lattice spacing, then we'd have to put here an A, the lattice spacing. And then in order to make, unfortunately now A goes to B times A. In order for it to not change under this rescaling, we have to multiply it by the dimensionless temperature to a power such that the combination A times T doesn't change, and that power is 1 over yt. So that means that the correlation length is proportional to T to the power 1 over yt. Sorry. In order to make it not change, it should be T to the power minus 1 over yt. Because T to the power 1 over yt still acquires a power of b. We want it to acquire a power of 1 over b. So correlation length is T to the power minus 1 over yt. So that means that this new exponent is 1 over yt. Okay? And from the data that I mentioned over here, for this phase transition, beta is 0.33 and nu is 0.63. So from this we can deduce that this phase transition described by a CFT for which YH is approximately 2.48 and YT is approximately 1.59. And if you recall what I mentioned before, that these couplings are space-time dimension minus the dimension of the operator, this means that this phase transition is described by a CFT with two relevant operators. One of them is OH, and one of them is OT. And if we do 3 minus y, we get that the dimension of OH is approximately 0.518, and the dimension of OT is approximately 1.41. And the amazing thing is that if you compute any other critical exponents and do similar arguments to these, you're going to find that all the other critical exponents are determined by YH and YT, and the measured values are all consistent. Okay? So, okay, so this phase transition CFT with only two relevant operators, and they have precisely these scaling dimensions. Let me mention why these y's are, why this formula is correct, that y is d minus delta. So right at the critical point, if we think about the two-point function of the operator, so at the critical point, if we think about the two-point function of the operator OH, for instance, OH of x1, OH of x2, this operator is dimensionless. It goes as a power of the distance. And let me write it like this. So it's x1 minus x2. In order to make it dimensionless, I have to put the UV cutoff. Okay. And the question is, what is the power? Now, in the action contains the integral d dx over a to the d to make it dimensionless times OH times h. Under the RG transformation, a goes to b times a, h goes to b to the yh times a. So that implies that this dimensionless operator goes to b to the d minus yh times OH. It's such that the action stays invariant. That works. So now, so under the scale transform, under the coarse graining, OH gets a power b to the d minus yh. On the right-hand side, we should write down a formula that acquires twice that power, because on the left-hand side we have two powers of O. So the thing that we should write here is 2 times d minus yh. So this is proportional to 1 over x1 minus x2 to the power 2 times d minus yh. So this is called Coup Delta. So delta is d minus yh. Okay. So hopefully it's clear how to connect these CFDs with RGs and beta functions. Questions about this?
So this OH is basically magnetization.
OH would be the magnetization in this case, yeah. Right, is the operator that couples to the temperature. I'll write down the Lagrangian for this theory, and it will be clear what I'll say what the operators are. Okay. So for the rest of today, I thought it would be good to have some explicit constructions of conformal field theories in 3 dimensions. Okay? So explicit constructions. In 3 dimensions. So first, I want to mention the idea by which, if we have a second order phase transition where some symmetry is broken, like in this case, there's a Z2 symmetry that's spontaneously broken on this side. The idea for constructing the field theory that describes this due to Landau and Ginzburg. The idea is to build a theory of the fluctuations of the order parameter. That's the thing that acquires a non-zero expectation value. So the Landau-Ginzburg paradigm is that we have some coupling, and at some point, as we vary that coupling, so for instance, in this case, it would be the temperature. At some point, we have a second-order phase transition. Below that temperature, we have an ordered phase, where the order parameter, so the order parameter, let's just call it M. In this case, it would be the magnetization for those magnets. So the order phase would have M not equal to 0. And above the temperature, or above that critical coupling, or on one side of that critical coupling, we have a disordered phase, where M is 0. So this works in this case. For this phase transition, we can construct the theory this way. I should mention that there are extremely interesting examples of conformal field theories in 3 dimensions that don't fall into this class. So there's very interesting examples beyond Landau-Ginzburg, where we have some coupling, we have a second-order phase transition, and we have an ordered phase on one side and an ordered phase on the other side with different order parameters. Okay. So it is possible to write down Lagrangians that have this property. And there are 2 different order parameters, and one of them acquires an expectation value on one side and the other one on the other side.
So in such a case, there's no phase transition because
No, there would be a second order phase transition. What's not true in that case is that the order parameters do not appear as fundamental fields in the Lagrangian. Only one of them does. The other one is something else.
So I'm a little confused. If
Yeah.
the order parameter itself changes, I thought that that's what tells us whether there'll be a phase transition or not, right? So the order parameter itself is changing as we cross the critical point. So how do we
It's a continuous phase transition. So there's one order parameter here that appears in the Lagrangian. As we approach the critical temperature, that thing goes to 0 as a power, and on this side it's just 0. And the other one does the other way around. It's non-zero here, goes to 0 at this point, and on this side it's 0. Yeah, so this is, for instance, what happens in lattice models between the nail and the VBS nail phase and the valence bond solid phase. And with Lagrangians, you can construct something like the CPN model. So scalars charged under a gauge field, and on one side there's a Higgs mechanism, and on the other side some monopole operators that condense. Okay? So for using the Landau-Ginzburg idea for uniaxial magnets, the order parameter is M. So we should try to construct the most general theory we can for this field M. So for the magnets, there's a Z2 symmetry. So there's a Z2 symmetry under M goes to minus M. So if we don't want to add a magnetic field, we should write down all possible terms we can write in the Lagrangian that obey the symmetry. So the continuum action is something like this, d3x, and we have a kinetic term. We have m squared, we have lambda m to the 4th, and so on. These are terms that obey the symmetry, and then if we want to break the symmetry by adding a magnetic field, we should write H times M. In order to be at the phase transition, so at critical point, we have to tune 2 things. So in the example of the magnet, one thing we have to tune is the magnetic field. We have to tune it to 0. That's easy because there's a Z2 symmetry. So we just set the magnetic field to be the value that's Z2 invariant. But then we have to tune the temperature. For the water vapor system, we have to tune two things. We have to tune the temperature and we have to tune the pressure. Okay? So for the critical point, we have to tune H and M squared. So tune H to 0 and tune M squared. As we change M squared, at some point we're going to have a critical point. Okay? So the way you should think about this action is as follows. So this is the rough picture of CFTs with Lagrangians. So how do we obtain how do we find a CFT with a Lagrangian description? Well, we have a UV where we have, in this case, we have a free theory. The UV fixed point of this action just has the first term. So the action in this case is just the kinetic term for M. And then, so we start with that UV Lagrangian, this. Suppose we, and then we could add a mass. We could add a mass, but we'd have to tune it, okay, in order to have a non-trivial fixed point. I'll say what happens if we don't tune it. And you just think of these as extra terms that we add to the Lagrangian, and these are relevant deformations. So we have a free theory plus relevant operators, and it flows in the infrared. So in the infrared, we have CFT. This CFT, I guess it's a matter of definition, but I could say that this could be a trivial CFT. What do I mean by a trivial CFT? As far as local operators go, a trivial CFT would have no local operators, just the identity operator. That's kind of a boring CFT. That's why I call it trivial. But this is what happens, for instance, if we don't tune the mass. We have an RG flow. In the UV, we have a free theory. In the infrared, we have a trivial CFT. There are no local operators. The scalar field has a mass. All correlation functions of M and powers of M decay exponentially. So at very large distances, we're left with nothing. Okay. So that's a rough picture by which I'd like to construct CFTs. So then let me just go through a list. So the simplest thing we can have is scalar fields. So maybe I should mention the ingredients for constructing Lagrangians from which we can find CFTs are scalar fields, fermions, and gauge fields. So scalars, that's the simplest example. The simplest CFT is one free, real, massless scalar. The Lagrangian is just a kinetic term, as I mentioned above. That is a CFT in itself. So this is CFT. It's got operators. The local operators are phi squared, maybe things involving derivatives. So for instance, d mu phi, and so on. Anything we can construct out of phi. the scaling dimension of phi is, in general dimensions, d minus 2 over 2. In 3 dimensions, that's a half. So this theory of a free scalar is a CFT in any number of dimensions, not just 3 dimensions. Correlation functions in this theory are computed using Wick contractions. So, for instance, the 2-point function of phi of x1, phi of x2, is 1 over 4 pi x1 minus x2. And all other correlation functions of all the other operators are computed using Wick contractions with this propagator. Okay. So as I said, we start with a free theory, and then we see how we can deform it to get non-trivial CFDs. As I mentioned, the first non-trivial way of deforming this is if we add a mass to the scalar. So 1/2 kinetic term plus m squared phi squared. Should think of this as an RG flow between this UV CFD and something else in the IR. And in the IR, it flows to, as I mentioned, a trivial CFD. So this isn't interesting. The interesting thing is when we have this Lagrangian 1/2 m squared phi squared plus lambda phi to the 4th. And so generically, if we don't tune m squared, we're in this situation. When I write 1/2 m squared phi squared, I mean plus also higher order terms in phi. So here, if we tune this, then we can flow in the infrared to a CFT. That's non-trivial. And this is precisely the CFT that I was describing before in these examples of the uniaxial magnet or the water vapor phase transition. So this is the Ising CFT. It has a Z2 symmetry because this Lagrangian that we started with has a Z2 symmetry. Symmetry phi goes to minus phi. And we could just think of this operator phi as flowing to some operator O1, where delta, the scaling dimension of O1, is 0.518. So that was one of the 2 relevant operators in the CFT. And phi squared goes to some operator O2 in the infrared, and the dimension of this O2 is approximately 1.41. Okay. This CFT is solvable in 4 minus epsilon expansion. So we can define it away from 3 dimensions, and when the number of dimensions is 4 minus epsilon, where epsilon is small, the infrared fixed point is very close to the UV one. It's a very short RG flow, and one can actually compute these scaling dimensions. I think people have gone up to 5 loops, if I'm not mistaken, for some of the scaling dimensions. And then it's an art extending that. The goal is to learn about the model in 3 dimensions, not in 4 minus epsilon dimensions, because we don't live in 4 minus epsilon dimensions. So then extending the 4 minus epsilon results to 3 dimensions is usually an art, because setting epsilon equal 1 is not entirely justified. But there are resummation schemes that give pretty good results. Yeah. Was that? Close to 4 dimensions. The reason for that is that the dimension of phi in arbitrary dimension is d minus 2 over 2. The dimension of phi to the 4th is the UV fixed point. It's therefore 4 times that, so that's 2d minus 4. So this in close to exactly in 4 dimensions, this becomes a marginal operator. And right below 4 dimensions, it's slightly relevant. And that's the reason why one can study this theory and Four-Mind subsonic expansion. So whenever we have, in general, if we have a CFT with a slightly relevant deformation, we can study that in perturbation theory. And the perturbation parameter is essentially the space-time dimension minus the dimension of that operator. Yeah. That's marginally irrelevant. Yeah. Okay. A generalization of this is, so this was one scalar. We have n scalars. That's the next most complicated thing, which is we can have a Lagrangian like this. So let's just say the scalars are phi I, where I goes from 1 to n. I should finish facing the board. And can write down this Lagrangian d mu phi I squared plus m squared phi I squared plus lambda phi I squared quantity squared, where I sum phi I squared means that I is summed over. So this theory has an ON symmetry. Okay. If we tune, if we tune all these operators away, we're left with a free theory of n scalars. That's a CFT. To get something more interesting, if we just tune m squared, then this theory flows in the infrared to a CFT with ON global symmetry. That's called a critical ON vector model. Okay. In this theory, all the operators transform in representations of ON. And so, for instance, phi I is a vector. Phi I quantity squared is in the trivial representation. Phi I, phi j minus the trace is in the traceless symmetric tensor representation, and so on. The reason why I'm mentioning this, one reason is that this is solvable at large n. And I think Igor talked about various large n limits. So this theory is solvable in that limit. What happens is that most operators have the same scaling dimensions approximately as in a free theory. So for instance, delta phi I, scaling dimension approximately a half, plus something of order 1 over n, and then you can just do, it's a series expansion in 1 over n, except for the operator phi I, and operators built from it, which in the free theory would have dimension 1 because phi has dimension a half, but at large n, it gets an anomalous dimension of order 1. So its scaling dimension would be approximately 2, plus order 1 over n. But for instance, phi I, phi j, where I'm not summing over I and j, this also has dimension approximately 1. So this 1 plus order 1 over n. Okay? So the only operator that behaves funny in this case is this phi I. Hopefully Igor explained how to solve these things. Can you introduce an auxiliary scalar? And it's actually that auxiliary scalar that plays the role of phi I in that description. Okay? So that's scalars. Then the next more interesting thing is fermions. What's interesting about 3 dimensions that doesn't happen above 3 dimensions is that one can have very non-trivial interacting theories with just scalars and fermions. In 4 dimensions and above, one needs gauge fields. So So for fermions, we can have, in 3 dimensions, we can have Majorana fermions, 2-component real fermions, real spinors. So for instance, if we have n free massless Majorana fermions, so the action would be psi bar, the Lagrangian would be psi bar I, d slash psi I. That's a CFT. By the way, this theory actually has very interesting global anomalies. I'm not going to talk about that. That's current area of research in 3 dimensions. The dimension of the fermion in arbitrary dimensions is d minus 1 over 2. And again, in this theory, one can compute correlation functions using Wick contractions. A more interesting theory built from fermions and scalars is to start with this theory and free massless fermions, add a scalar phi, and then have the following thing. So have the Lagrangian be this: psi bar I, d slash psi I. And then for the scalar, we can have a kinetic term, d mu phi squared. We can have m squared phi squared. This one we tune. We can have a quartic term, lambda phi to the 4th. And so far we haven't done much because this is just, they're not interacting. But we can add a Yukawa interaction, phi psi bar I psi I. And the claim is that this theory, if we tune m squared, this flows in the infrared to a non-trivial conformal field theory. So RG in the infrared is a CFT. And this is called the Gross-Neveu-Yukawa model. Okay? And it also has ON symmetry. Yeah? No, I think it makes sense. Smaller n as well. Even down to n equal 1. I think when n equals 1, it's believed that this theory has emergent supersymmetry in the infrared. And emergent n equal 1 supersymmetry. So that's a minimal amount of supersymmetry in 3D. So since that's the belief, then it makes sense down to n equal 1. But it's again solvable in large n. Okay? So then one can construct much more complicated things, which are scalars and fermions. Can make supersymmetric theories and so forth. Okay? 2 minutes? Okay. So let me just then say a couple of things about gauge fields. If we just have so free scalars is a CFT, free fermions, that's a CFT. How about a free gauge field? This action 1 over 4e squared, Lagrangian f mu nu, f mu nu. That's a kinetic term for a gauge field. This is not a CFT. So f mu nu, everybody knows, is d mu a nu minus d nu a mu. This is not a CFT. Because a CFT is a theory without scale, but in this case, the gauge field has dimension 1, f mu nu therefore has dimension 2, f mu nu squared therefore has dimension 4. So that means, in order for the action to be dimensionless, that E squared has dimensions of mass. So E squared has dimension 1. So it's, what's that? It's not a trivial CFT. I'll explain that because this this ends up being dual to a periodic scalar field. And the CFT that it describes in the infrared is one free scalar. Okay? And right, yeah. If you try to couple it to matter, then A would appear in the action next to a derivative. So I'd have to mention one. Okay, but if we add matter, then we can get non-trivial CFTs. Okay? I will mention that at the beginning of the Monday lecture. Okay? It's probably a good time to stop.
Questions?
Yeah, what did scaling the IR? And just have purity.
So you can write down this F mu nu is epsilon mu nu rho d rho phi for some scalar field phi, and then the action, could just replace that, put that in there, and you get that the action is just d mu phi squared. It's a little trickier than this, because if the gauge group is U1, then what happens is that this scalar phi is periodic. Sorry, so maybe I can just make the units work out. So I think I need to put here an E squared. And one can show that phi is identified with phi plus 2 pi. Okay. This in itself is not a CFT, but there's a U1 symmetry, that this theory has a U1 symmetry that it breaks spontaneously. And if we expand around one of those vacua, then the theory is that of a non-compact, non-periodic scalar, and that's just the same thing as like one free scalar field that's massless. That's what I would say about this theory. So the way to think about the Maxwell theory is essentially as an RG flow. It's got a dimensional full coupling in it. It's an RG flow, and in the IR, there is it spontaneously breaks a U1 symmetry that I'll mention on Monday, and right, and there's a CFT, rather trivial one. Yeah.
So you mentioned that the systems are similar. So is that an exact statement that the CFT as the constant or
Sorry, the statement about universality?
Yeah.
Just the phase transit, the critical point that's described by the CFT. Not the full system. Not the full system.
Right,
Yeah. Only the critical point. Yes.
Yeah, of course. But it makes sense to scale dimension for.
Yeah. If you can solve, for instance, the lattice model and compute the scaling dimensions precisely, those are the scaling dimensions precisely of the water vapor critical
What
point.
about the scalar distribution of those models? So
Same. If you can solve it, yes. That's just a continuum limit of the lattice model. If you can solve that and compute the scaling dimensions exactly, then those are that is the answer. Yeah.
So for the one case, we can do this.
Yes. Yes. Right. Well, I would say that if you just have the theory without matter, it's again not a CFT for the reason that in this case, instead of E squared, you'd have the Yang-Mills coupling. Yang-Mills coupling would be dimension-full again, and that's not a CFT. But when you add matter to it, then it can flow to a CFT. You see, this term here is actually, this is a dimension-full coupling, but this term has dimension 4. So if somehow there were other terms in the action, then this would be irrelevant at the infrared fixed point. So we could just drop it. The Chern-Simons term, the situation is different. That one actually matters in the infrared. If you just have a Chern-Simons theory, I would say that is a CFT. It's just a trivial CFT in some sense. It doesn't have any local operators. It has interesting non-local operators, but doesn't have any local operators. And again, you can add matter to it, and you can make interesting CFTs. Or you can add both this term and the Chern-Simons term. Yeah.
So let's say switch to just actual theory has multiple acids that fine.
That depends on the what the theory is. So right. So it depends on what the Lagrangian is precisely. If you get it from a lattice description, typically what happens is that you don't just have this term in the action, you have this term plus monopole operators. In terms of this scalar field, the monopole operators amount to some cosine potential. And then the theory confines. And it's no longer, in the infrared, it's no longer a free scalar. It has a trivial vacuum. Okay, so that one, if the monopole operators appear in the action, then there's no spontaneous symmetry breaking. There's an explicit symmetry break. I should have defined the symmetry that I'm talking about.
So maybe that's a good
Yeah.
place to take our break. Thanks, Silviu, again. So the last session of the day will be discussion. Silviu's here, Miranda's here. You can ask questions for the two of them, and then I won't be here for it, but have a wonderful weekend.